Alright, in this video we're going to talk about calculating moments of inertia. So this is a concept from physics. If you've had physics, maybe you've calculated these before. If not, that's okay. We're really going to focus on the integration associated with this. Alright, so there's a little description here. Moment of inertia describes tendency of an object to resist rotation. So an object with a larger moment of inertia, harder to rotate. So think about holding a stick from one end, a very long stick. It's maybe hard to rotate versus if you hold it close to the middle, easier to rotate. That would have a smaller moment of inertia. And the other idea that you might have seen from physics, kinetic energy of a rotating object is proportional to the moment of inertia about the axis of rotation. All right, so that's some ideas about what this calculation is that we're going to calculate, but we're going to focus here on setting up the integrals to calculate it. So we've got some formulas here for my class. These are not formulas I would expect you to memorize. I would expect you to be able to use them if you're provided these formulas to calculate moments of inertia. All right, so for two-dimensional surfaces, we have all these double integral formulas, and then for three-dimensional solids, we've got these triple integrals. We have an example here at the bottom that talks about a flat metal plate in the shape of a triangle. So we're going to assume that that's a two-dimensional surface with a density function given. We're going to find a moment of inertia of the plate about the line x equals 1. So looking up here at these formulas, the one that we are going to need is the moment of inertia about a line, and the r part of this equation is the distance from a point xy to a line L that I'm rotating around. Okay, so I've written down the formula for a moment of inertia that we need for our particular problem here, and I've drawn a picture of our region, a triangle with vertices at 0, 0, 1, 0, and 1, 1. We have a density function given by this function, so that would mean that our density of this object is larger the farther we get from the origin. And we want to find the moment of inertia of this plate about the line x equals 1. So the line x equals 1 would be right here at the edge of this plate. So when I write this part here, that is the distance from a point xy to the line that we are rotating about, we want to think about representing that distance right there. That's what that r would be. All right, so that distance would be different for different points in this region. So I need to write an equation that depends on a variable. Okay, so this r that I have here is going to be the distance from the line x equals 1 to some arbitrary point xy. And you can see that that distance across there is really measured in the horizontal distance. It doesn't matter what the y coordinate of that point is. It's really focused on the x coordinate of that point. What I've done here is write an expression for the difference between 1 and x. So I took the larger minus the smaller to think about that. So that's going to be my r. I'm going to go ahead and set up my integral. We want to think about whether the region is x simple or y simple. It is both. I'm going to go ahead and set this one up with dy on the inner integral. So I'm going to think about going through that region in the direction of increasing y to set up my inner limits of integration. We'll enter at y equals 0, and then we'll leave through the equation of this line that goes through 0, 0, and 1, 1. So that one's pretty easy to write down. That's y equals x. Our x limits of integration will go from x equals 0 to 1. The r was 1 minus x. Don't forget that that's going to be squared. And then our density function. This is one where we might think a little bit about whether we would prefer to use polar coordinates. I don't have a circle centered at the origin, but I do have a line that's through an angle, pi over 4, and an angle at 0. And I have an x squared plus y squared in my equation. So you might think about using polar coordinates, but I think this one actually turns out a little bit easier in just rectangular coordinates. All right, I'm going to go ahead and do my first integration with respect to y. And there's some easier ways or some harder ways to do this. So I just want to talk a little bit about some more efficient way to do this problem. An inefficient way to do this problem would be to expand that whole thing out and then integrate with respect to y. But if you pay attention to what's going on here, when you integrate with respect to y, this factor is being held constant. So that's just like a constant that will come along out front, just like if you had a 5 or something like that. And then I'm just integrating this second factor with respect to y. So x squared times y plus 1/3 y cubed. All right, so I plugged in my limits of integration. x and 0, and I might notice that what I have left in this second parentheses simplifies to 4/3 x cubed. And then I need to go ahead and integrate. At this point, I probably will go ahead and expand out my 1 minus x, the quantity squared, distribute through my 4/3 x cubed, and then it's pretty easy to finish that integration. Okay, so you can see here I've done the integration with respect to x. I've plugged in my limits of integration, and now I need to just simplify my answer. Okay, so I got a numerical answer here. The other important thing about this would be to think about units. I wasn't really given any units in the original problem, just a density function and some distances without units. Our textbook does that a lot. In physics, if you think about sort of unit analysis, the density function would be mass per unit area, and then I have area here, and then this is a distance squared. So if you think about the units here, we would end up with mass times distance squared. So in physics, a lot of times you might see that labeled as kilogram meters squared. All right, do some practice problems like that.